In this video, we're going to start the video with the chapter 11. We're going to start the class from chapter 11, atoms. All the matters are made of atoms. Atoms are the basic units of matter. However, these atoms are very, very, very small. So the size of atoms ranges from 10 to the minus 10 meter to 5 times 10 to the minus 10 meter. What does that mean? The size of the hair diameter is 10 to the minus 6 meter, micrometer, in a range of micrometer. So it's the size of the hair is 10 to the minus 6 meter. And the size of atom is 10 to the minus 10 meter. So as you can see how small the atom is, maybe. All right, so the visible light that we see in our eyes, what we can detect in our eyes, visible light has a wavelength that ranges about, let's see, push it 300 nanometer to 800 nanometer. What's that mean, right? 300 times 10 to the minus 9 meter to about 800 times 10 to the minus 9 nanometer. And 300, yeah. So 300 times 10 to the minus 9 makes it about 3 times 10 to the minus 7 meter. And I mentioned that atom is 10 to the minus 10 meter. So, and that's the size of the wavelength, the visible light. Think about that waves on the ocean. You have a waves that's a wave that makes up and down about this distance, this wavelength, right? And imagine having a tiny, tiny, tiny grain of sand. That's, so this is like 1/10,000 smaller than the size of the wave. Does this wave feel that tiny, tiny, tiny grain of a sand? That's 1/10 of a 10,000 of a size of this compared to the size of the wave. This wave don't feel anything, right? So the visible light won't detect it. It won't catch it. The size of atom. We can't observe. We cannot see the atom because the size of atom is so small compared to what we can see. All right, so we can't see. No matter how good the microscope we make, we can't see. So if that's the case, why we say that, how do we prove the idea of atoms? Why we say, how could we say? So the idea of atoms was around, but nobody could really prove it. Before we get into it, let's talk about the characteristic of atom first. So I'm going to share the screen. Here. Ideally, I'm writing down with you, but I already written down, so here it is. So chapter 11, atoms. And as I mentioned, that atom is one of the basic units of matter. And the size of the atom ranges from 0.1 nanometer to 0.5 nanometer. That's about 1 times 10 to the minus 10 meter to 5 times 10 to the minus 10. So it's the size of the atom. So we even have a special unit for 10 to the minus 10. So you can write A and a circle on top. That's called angstrom. That represents 10 to the minus 10. So that's how small the atom is. If an atom is that small, to make up a gram of water, that means there has to be 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and a 0, 0, 0 amount of atoms in a gram of water. 10 to the 23 atoms that's in the water. So that's how small the atom is. So that's why how much abundant the atom is to make up a matter. And these atoms are constantly in motion. You can think about it as a temperature, for example, room temperature. That means that you have some kind of a thermal energy temperature. And because you have a thermal energy, you can convert it into like a kinetic energy, like motion, energy of motion, right? So then, so for example, gas, let's see if I can add it here. If you have a, if you have a gas particle, that means that the atoms are moving from one location to another location, very long, large distance. And even a liquid, it's okay. Even a liquid, atom moves one location to another location, but it's not as much, not as large distance as the gas atoms, gas particles. But when the materials are in a solid state, so they're bounded tight, but they're still, you have a room temperature. For example, this pen is a solid material, but it has a room temperature, right? So even though it's solid, they're bounded tightly with each other, but they're still vibrating. Still, they vibrate in place. So they're constantly in motion. So as you can see, even in a solid matter that's made of atoms, that's bound, tightly bounded, but they're still constantly in motion. So these atoms are constantly in motion. So these are the characteristics of atoms. Size is very small, 10 to the minus 10. And then because they're so small, there's so many of atoms, and then they're constantly in motion. Also, another things about atom is that they're ageless. That means that typically, if they don't decay quickly, if they're not unstable, they tend to be in that atom for a long time. You can fuse them or you can do stuff about it, but they tend to stay in that element for a long time. Okay. So those are the characteristics of atoms. And I say, again, I mentioned that atoms is so tiny and we can observe it. And how do we prove the existence of atoms? So it was in 1827, there's a British botanist called Robert Brown, was observing pollen suspended in the water, liquid. So he was looking through the microscope, that's pollen that's suspended in the water or the liquid. And then you see these pollens that's making a motion. Let me show you how it looks like. No computer sound. Yeah, no computers. Yes, computer sound. All right. So as you can see on the screen here. So these dots are the pollens. So you see these pollens are moving in a weird way. And people couldn't explain this motion for a long time. You see this big particles that's moving around and making a weird motion, but do you think this pollens has its own mind to move to make this kind of a motion? Strange, right? So here, Albert Einstein is the one that came and explained this motion that's called the Brownian motion, the random motion of microscopic particles in a fluid. That's explained by the Albert Einstein that says that there are smaller invisible particles that's so much smaller that we can't see, but they're constantly being collided. And these little collisions, the thousands collisions by these small particles are making this big pollen move. So it's due to the collision from the atoms that we can't see, a lot smaller particles. And this motion is called Brownian motion. And this is the evidence of atoms because we can't directly view the atoms. I'm going to share the slide now. Here. So chapter 11, atomic nature of matter. This is about atoms. And all matters are made of atoms. And what is atoms? Atoms are tiny particles that move around constantly, motion, attract each other when they're in a small distance. And if you squeeze into one another, they may want to go apart. So before atoms, people were categorizing the materials into 4 different elements: earth, air, and fire, and water. You don't need to know these things. And then let's say if the object belongs to earth, for example, you move it up, right? Then it wants to go back to earth. So that's why it drops. That's how people are explaining it. And but people's been wondering about the idea of atoms, but nobody could really prove it. And in 1827, Robert Brown, botanist, was observing these pollens that's in the water. And later, this idea was confirmed by Albert Einstein that it is, in fact, the evidence of atoms. So it's the smaller particles that we don't see that's constantly in collision with the bigger particle, that pollen that we can see. Let's see, I can show you. I'm going to show you the video here. So here is simulation. The black dots are something very small that's constantly colliding with the yellow one. And the yellow particles is what we can see, and it makes a random motion due to the random collisions by the smaller particles like atoms. And what's this motion is called? The characteristic of atoms is atom is very, very tiny. What's the size of the atom? Well, you don't need to memorize the number, but I want you to get an idea that it's very, very small. That's 10 to the minus 10 meter, which is a lot smaller than the diameter of a hair, and even smaller than a visible light that we can see. And because it's so small that it's numerous, you're going to have, even just to make a gram of water, you need 10 to the 23 atoms in a gram of water. There are 10 to the 22 atoms in a liter of air. It just sounds a lot, right? And I wrote down how many zeros. So, and these atoms are constantly in motion. Even the atoms that's making a solid matter, even though they're boundedly tight, they're still in motion. And I say ageless. It is ageless. It just stays there. It's in that form of atom, unless you chemically make a reaction or do something to it. There are some atoms that's unstable and decays. All right. Let me see. So I mentioned that atom is so small and smaller than a wavelength of a light. And imagine that if you have this size of the wave and then tiny, tiny dot to it, this wave won't feel anything. But if you have the size, the wave, but then if you have the size of the matter, so the wavelength and the size of matter that you want to see has to be comparable to each other to observe. However, so with the new technology, the visible light is about 300 nanometer to 800 nanometer-ish, I mentioned. 10 to the nanometers, 10 to the minus 9. So 300, 10 to the minus 7-ish. But there is electrons that's smaller than a visible light. Electron is smaller. So using electron beam, we can actually observe atom. So here you use you shoot the electrons and then you can see the atom. And this is the image of a STM, scanning tunneling microscope image of atom. So you have you make a very clean surface, flat surface, and you make a pattern like this, ring pattern. It's easier to observe, right? So you on purposely make this kind of a shape so that you can observe it easier. And then you shoot out electrons and scan it throughout the surface, and then you can detect this bumpiness because electron is a lot smaller than an atom. So this electron can actually detect and come back. So this is the STM image of the atom. So now we can see the atom because we know that there is a smaller particle than an atom, which is electrons. But at that time, when we couldn't have this, we didn't have a technology, it was hard to prove the existence of atom. And then what proved the existence of atom? Right, Brownian motion. All right, so it should be enough for this video. In the next video, I'm going to talk about atomic structure.